In February 2013, asteroid 2012 DA was nearing the Earth. Telescopes had been tracking the space rock for almost a year, and its orbit was understood. It would miss the Earth by around 30,000 kilometers. At the same time, another asteroid was approaching, but nobody had seen it. It entered the Earth's atmosphere above Russia, passing to the south of Kamensk-Uralsky and directly over Chelyabinsk. People flocked to windows to see the dual smoke trail, unaware that the meteor had exploded 30 kilometers above the ground. It took more than a minute for the shockwave to arrive, when thousands received injuries from shattering glass. This was not the first asteroid to hit the Earth, and there will be more. The largest asteroid orbiting within our solar system is Ceres. Discovered in 1801 by Giuseppe Piazzi, it was thought to be a new planet. It orbited between Mars and Jupiter, where astronomers thought there should be another planet. William Herschel, the discoverer of Uranus, decided there was something strange about Ceres. No matter how great the telescope magnification he used, it could not be seen as a disk like the other planets. It always appeared as a point source, like a star. So he called it an asteroid, meaning star-like. During the 19th century, more and more asteroids were discovered, all orbiting between Mars and Jupiter, with this region becoming known as the asteroid belt. Modern estimates have more than 1 million objects at least 1 kilometer across in the asteroid belt. Today, the most widely accepted theory views the asteroid belt as remnants from the formation of the planets. The huge gravitational influence of Jupiter confines them to a band, and Jupiter's orbital velocity imparts great speed to the asteroids. They travel too fast to form larger bodies, with any collisions resulting in fragmentation. In orbits beyond Neptune, known as the Kuiper belt, there are different, much colder fragments. These are also remnants from the formation of the solar system. They are composed of frozen methane, ammonia, and water, with some rock. Because of their extreme distances from the Earth, these bodies are generally difficult to observe, but sometimes Neptune's gravitation will nudge one toward the Sun. These are comets. Nearing the warmer regions of the solar system, a comet's ice sublimates, forming a coma many times larger than its solid core. The coma resembles an atmosphere that is not gravitationally connected to the core. It is blown out by the solar wind to form a tail. Comets have been recorded since ancient times. During the formation of the solar system, a disk of gas and dust swirled around the young sun. Small particles in this disk, called chondrules, coalesced into larger asteroid-sized pieces which continued to grow, establishing the protoplanets. Planets in the inner solar system were pelted with debris as the expanding giant planets set up orbital resonances, disrupting the paths of the asteroids and comets. This period, known as the Late Heavy Bombardment, is thought to be when the Earth received its oceans. The heavily cratered surface of the Moon shows obvious scars of asteroid impacts. But had the lunar craters accumulated over time, or were they the result of a narrow period of great turmoil? Evidence supporting the late heavy bombardment grew out of research on the lunar samples returned from the Apollo missions. The age of impact materials seemed to fit into a narrow time frame. For 2 more decades, asteroids and comets remained nothing more than faint moving dots only visible through a telescope, unless they decided to show off, a comet by approaching the Sun and developing a tail, or an asteroid by entering the Earth's atmosphere, becoming a meteor and burning up.
4, 3, 2, unité, top.
But in 1985, the European Space Agency launched its first deep space probe, Giotto. It was headed toward Halley's Comet. Mission planners wanted Giotto to enter the comet's tail. Though it was equipped with a protective shield, designers expected the spacecraft to suffer terminal damage from the debris clouds surrounding the comet Halley. There were other probes targeted at Halley. 2 Soviet Vega spacecraft would drop landers at Venus, then loop back toward the comet, and 2 small Japanese probes would also observe. All space agencies had agreed to share their data. Accurate tracking information from the Soviet probes was essential for Giotto's navigation toward Halley's nucleus. It approached Halley at a relative speed of 68 kilometers per second. At slightly less than 8 million kilometers, its instruments began sensing hydrogen ions. 2 hours before closest approach, Giotto's sensors began registering impacts from dust. Most were the size of the particles in smoke, but some were bigger. At less than 600 kilometers from the nucleus, a particle weighing 1 gram sent Giotto spinning out of control, and all contact with Earth was lost. Engineers on the ground feared the worst. After half an hour, the signal from Giotto returned. The spacecraft had stabilized itself and continued to transmit valuable data. We learned that the comet had formed 4.5 billion years ago, as different gases froze around dust particles. It was the first solid evidence that comets, and probably asteroids, were largely unchanged since the formation of the solar system. In 1989, the Galileo mission was launched. It was targeted at Jupiter, and to get there, it would pass through the asteroid belt. In 1990, from a distance of 1,600 kilometers, Galileo focused its cameras on 951 Gaspara, capturing the first ever pictures of an asteroid. Spectral analysis revealed a stony S-type composition. Galileo looped back past the Earth for a gravitational assist before re-entering the asteroid belt. It observed 243 Ida, discovering that it had its own moon, which was promptly named Dactyl. Both were similar in composition to Gaspara, resembling the ordinary chondrite meteorites found on Earth. But researchers wanted to get their hands on material from the orbiting fossils to carry out more detailed analysis. This was the beginning of asteroid geology. But from the rocks on Earth, new information about asteroids was grabbing attention. Physicist Luis Alvarez, with his geologist son Walter, had discovered that one distinctive layer of sedimentation found all around the world contained exceptionally high levels of the element iridium. While iridium is rare in the Earth's crust, it is common in meteorite samples and therefore in asteroids. In addition, this sedimentation layer marks the boundary between rock laid down in the Cretaceous period, when dinosaurs were abundant, and the Paleogene period, when dinosaurs were extinct. The implication was that a large meteor strike had wiped out the dinosaurs, and while science was aware that asteroids still struck the Earth, the idea of one large enough to trigger mass extinctions was sobering.
5, 4.
In October 1998, a Delta II lifted
1.
off.
Main engine start and liftoff of the Delta rocket with Deep Space One, testing the spacecraft technologies of the next century.
Though interest in closer analysis of asteroids and comets was intensifying, it was realized that rendezvous with them was difficult. NASA knew that this type of mission would either be really expensive or new technologies would have to be developed. Deep Space One was targeted at asteroid 9969 Braille, but its primary objective was to test a range of experimental technologies. It was the first mission funded by NASA as part of the New Millennium space program. Deep Space One was NASA's first probe to use ion propulsion. Its ion thruster expelled the inert gas xenon using power from a new generation of solar panels. Deep Space One had an autonomous navigation system. Rather than tie up the very busy deep space network, it could plot its own course. Its contact with asteroid Braille was disappointing. A last-minute software crash and the asteroid's blackness meant the images returned were indistinct. Yet after the encounter, the spacecraft's reserves of xenon were still plentiful, and mission planners confidently redirected Deep Space One for a rendezvous with Comet Borrelli. In September 2001, Deep Space One reached the comet. Its images of Borrelli were clearer than Giotto's pictures of Halley, and even though it had no protective shielding, Deep Space One missed Comet Borrelli's emission streams and sustained no damage. The mission was judged a success, but given its primary goal was to test new hardware, researchers were no closer to understanding the primitive chemistry of comets. Stardust, launched in 1999, was a mission designed to return cometary samples to the Earth. It visited Comet Wild 2, a body newly dislodged by Jupiter. It unfolded a tennis racket-like grid to catch dust spewing from the comet as it approached the Sun. In 2006, its sample return capsule entered the Earth's atmosphere at record speed, landing safely in the deserts of the American state of Utah. The minute particles it returned to the Earth were found to be forged in intense heat during the formation of the solar system. Then they had migrated to the frigid regions. There were traces of glycine, an amino acid. In addition, Stardust had captured 7 grains of dust that had come from outside the solar system. Now, researchers wanted to study the stuff that made up a comet's nucleus, rather than just the material that came loose when it was heated. To do this, the Deep Impact probe would use brute force. In 2005, it released an impactor on a collision course with Comet Tempel 1. It transmitted images back to the mothercraft during its final seconds. The impactor hit at more than 36,000 kilometers per hour, leaving a crater 150 meters across. From a distance of 500 kilometers, the Deep Impact mothercraft recorded images of the swirl of ejected material. Orbiting telescopes, such as Hubble, Chandra and Spitzer, also focused upon the impact with Comet Tempel 1. Spectral analysis revealed more dust and less water than expected. The dust was fine, like talcum powder, with the comet's nucleus loosely packed being 75% empty space. The Deep Impact Science team was delighted with the results, and after the flyby of Tempel 1, their spacecraft still had abundant reserves of fuel. It was decided to send the probe on a new mission to the very small comet Hartley 2. It was interesting because it appeared to be losing more water than comparable comets. Deep Impact, now renamed Epoxy, approached Hartley late in 2010. By now, the engineering team was becoming familiar with the techniques needed to rendezvous with a comet. Because their orbits vary due to their changing masses and outgassing, it's practical for the spacecraft to use its cameras and navigate autonomously. Nearing closest approach, the probe began sending back the clearest images of a comet to date. Frozen CO2 deep inside the nucleus turns to gas, forcing chunks of ice and dust out into space. But they move so slowly that they fall back to the surface. Every comet observed from close quarters appeared unique, and the more researchers learned, the more new questions arose. After a sample return mission and a mission to slam into a comet, the next cometary probe would set the degree of difficulty far higher by landing on the face of a comet. On the 2nd of March 2004, the European Space Agency launched its most ambitious space mission to date. The Rosetta probe would not just fly past a comet, it would rendezvous with 67P Churyumov-Gerasimenko near the orbit of Jupiter before it had developed its coma.
When I first heard the idea of Rosetta, I thought it would be extremely difficult.
We've never flown a spacecraft to a comet.
Rosetta would follow it in toward the Sun to observe the comet's changes. It was also equipped with Philae, an extra probe that would land on the comet. It would take 10 years for Rosetta to reach Comet 67P, and it made a series of close passes of Mars and Earth to gain gravitational assistance. It was the first probe, operating at such vast distances from the Sun, to rely upon solar panels for its power. Rosetta had originally been targeted at Comet 46P Wirtanen, but launch delays caused by an earlier failure of an Ariane 5, the same type of booster intended for this cometary mission, meant that the narrow launch window had closed. The complex trajectory had to be reformulated very quickly, so Rosetta could still carry out the same type of mission, but with Comet Churyumov-Gerasimenko as its new destination. But there was a problem. The lander had to be modified. The new comet was twice the size of the original. To cope with the higher landing speed that was now expected, Philae's impact-absorbing legs had to be strengthened. Executing a good landing worried mission planners. While Philae would approach the surface at low speed, it could easily bounce back into space. To prevent this, there were both harpoons and ice screws in its feet, designed to hold onto the surface, and a cold gas thruster would also stop any rebound. It would be 10 years before Philae's design engineers could see the surface of their comet, and in the cruise phase there would be other things to worry about. During its transits through the asteroid belt, Rosetta flew past 2 asteroids. In September 2008, the spacecraft sent back a series of images of asteroid Steins. It was able to plot its orbit accurately, and it determined that Steins was a rubble pile rather than a monolith. 2 years later, it flew past Lutetia, a minor planet. It is one of the most dense asteroids known, with a heavy metallic core. In 2011, as Rosetta was heading into deep space beyond the orbit of Jupiter, the spacecraft was put into hibernation. At these distances, even with 64 square meters of solar cells, Rosetta did not have the power to keep its systems running. All electricity was devoted to warming its instruments and its thrusters.
We had to switch off most of the systems, spin up the spacecraft, and leave it alone. Since the 8th of June 2011, we have no signal from the spacecraft. This was planned. It's not something that we like doing, but this is really what the last 2.5 years were about.
Rosetta's internal clock was due to wake it up on the 20th of January 2014, and a large group had gathered at the European Space Operations Centre. At this point, 673 million kilometers from the Sun, the spacecraft was now close enough to resume functionality. Though ground engineers understood what should be happening, they still had no contact with the spacecraft. Upon the command from its timer, Rosetta began a sequence of events. Its star trackers were switched on and began to reach operational temperature. 6 hours later, thrusters fired to arrest the craft's rotation. Rosetta determined its attitude and pointed its high-gain antenna at Earth. Only then did it send a signal.
This signal is just a beep, single beep, but if we hear it, then it means the spacecraft has done its job up to that point, and it's up to us to do the rest.
Both NASA's deep space dishes at Goldstone in California and at Tidbinbilla near Canberra were listening for Rosetta to make contact. The technicians and dignitaries assembled at the Space Operations Center knew to the second when Rosetta's signal should arrive, but nothing happened. In deep space, Rosetta's computer had had to reboot. The signal had arrived, 18 minutes late. Some had devoted 10 years of their lives to the project.
Getting it back is incredible. It's really, now we have one of the most fantastic adventures in front of us, one of the most challenging space missions ever.
At this stage, Rosetta was still 9 million kilometers from the comet, and ground staff still had a lot to do to prepare the craft. First, software updates were transmitted to improve its communication speed. And as it continued moving closer to the Sun, Rosetta's scientific instruments were switched on.
After a few weeks, we will be at a distance that will allow one of the most powerful telescopes we have on board to detect the comet. And this detection is very important because it will allow us to target our maneuvers to the right direction.
In May 2014, the first of 10 orbital correction maneuvers was executed. These were complicated by a pressure leak in the fuel tank repressurizing system that became obvious in 2006. The thrusters were operated at reduced efficiency to compensate. Soon, Rosetta could see Comet 67P. As previous cometary missions had discovered, the uncertain behavior of comets makes it desirable for a spacecraft to guide itself during the later stages of rendezvous. By July, the craft's navigation camera was returning clear pictures, and researchers were starting to see what Comet Churyumov-Gerasimenko looked like. The team charged with landing the Philae probe on its surface began to worry. The comet was not the potato shape they had been expecting.
Operationally, we have to consider whether there's enough sunlight, temperature aspects, which are also driven by sunlight, and the capability of actually getting the lander trajectory to enable it to land where you want it to. The comet itself has effectively two lobes, a small lobe and a big lobe. One of the questions we were asking was whether one would be better than the other in terms of science. There were discussions as to what the surface was like to give us an indication of perhaps processing, so younger material on the surface or older material on the surface. That would mean that we might want to avoid a particular part of the the comet because the upper layers were too deep. They didn't have enough primordial material for us to reach with a drill on the lander. So this kind of thing was traded from the scientific point of view.
Though the comet had very low gravitation, its peculiar shape meant that its gravitational field would vary greatly, making Philae's landing more difficult.
If the descent works, the landing is okay, we receive a sample, and the whole thing runs smoothly, that would be just great. But we need a lot of luck, really. And we had a lot of luck already.
By September 2014, Rosetta had reached the comet. Its first task was to carry out an exhaustive survey of the surface. Rather than go into a conventional orbit, the probe made several triangular maneuvers at distances between 50 and 100 kilometers. The primary objective of this survey was to find possible landing sites for the Philae probe.
Once the two prime landing sites are selected, the nominal one and the backup are selected, then we have to design the operational part of the whole thing. They've been selected by scientists, they've been pre-checked from an engineering point of view, but then we have to transform these wishes, these intentions, into something that is doable. First thing we have to do is to design an orbit for the spacecraft to fly around the comet and to be phased with the comet such that we can deliver the lander onto this place.
Finally, Site J on the head of the comet's smaller lobe was selected as the primary landing site. In November 2014, Rosetta was on course to swoop past the comet along the line of its rotation. At this point, the probe was still 500 million kilometers from Earth, and signals would take 28 minutes to reach mission control. Philae was released 25 kilometers above the comet's surface. Descending at 1 meter per second, it took 7 hours to touch down.
So we can't be happier than what we are now. We definitely confirmed that the lander is on the surface.
Although there was great excitement in Darmstadt, things were more complicated than they had at first appeared. Philae's harpoons had not fixed it to the surface as planned, and the cold gas thruster designed to keep the lander down had not fired. Philae had bounced twice before settling on its side in a shaded area. With very little sunlight falling on its solar cells, the main battery could only power the lander's instruments and communications link for 60 hours. After the situation had been fully understood, scientists had around 12 hours to collect the data and carry out further detailed analysis. Philae relayed an image of its surrounds with one of its landing legs in the foreground, which helped researchers locate the craft, but it was unable to collect and analyze a soil sample. The probe carried 10 different instruments to gather information about the surface, the radiation environment, and isotope ratios, amongst other things. Each subsystem was backed by the group that built and operated it. A team from the Max Planck Institute in Göttingen was responsible for the COSAC experiment, a combination gas chromatograph and mass spectrometer. A duplicate instrument sits inside a vacuum chamber at the institute.
The sample would have been great. Then again, the whole sequence worked. I mean, after 10 years in flight, the whole instrument behaved as it should have done. So everything which was under our influence, what we built, what we did, what we planned, programmed, tested, did work, just that the comet wasn't quite as cooperative as we would have hoped.
As expected, the lander, without sunlight, soon went quiet. But as the comet continued toward the sun, there were expectations that the increase in illumination might revive Philae. Yet the science team had still gained a lot of information.
By the first landing on the comet, we learned, of course, also about the physical properties of the nucleus. We found out it is very hard surface, almost like ice, porous ice. And this, of course, is important information for whatever future mission we would plan, which would land either on a comet or even go a step further and try to get samples, maybe even a core from the surface in order to return it back to Earth.
As Churyumov-Gerasimenko moved toward the Sun, the Rosetta mothercraft was traveling with it, returning a steady stream of data. Pictures revealed an alien landscape of rugged cliffs and boulders. Yet with gravitation 1/10,000th of what we experience on Earth, it is a fragile environment. And on the surface there was surprisingly little ice. Philae had learned that the surface was covered in up to 20 centimeters of dust. Beneath that was a blend of solid ice and dust. Rosetta recorded the changing nature of 67P. As it began to warm, jets of gas, dust and water vapor appeared. In Darmstadt, ground engineers frequently had to change Rosetta's course to avoid damage from cometary debris.
We control Rosetta twice a week. We check where it is in its orbit, in its planned trajectory. We see the effects of the environment of the comet to the spacecraft. So twice a week, we decide what to do, and we keep doing it. There are weeks where nothing happens, and we continue with our plan. There are weeks or weekends where something dramatic happens. It happened a few weeks ago, and we had to change the distance from 200 to 300 kilometers. And this is something you have to plan within a day. We have to react and be able to do it.
As the comet made its close approach to the Sun, it transformed. Sinkholes opened, and boulders tens of meters across were thrown hundreds of meters. Whole cliff faces collapsed. What looked like blizzard conditions broke loose across the surface. A big surprise was the abundance of molecular oxygen in the coma. Current theory predicted that free oxygen would have reacted with hydrogen to form water as the solar system formed.
We're seeing features that you would associate with terrestrial analogues. So we're seeing features that would be driven by winds, features that are reminiscent of what you see on the beach. But you have to be careful to make those direct comparisons because the environment is it's so alien, it's so different. The gravity is much lower. The gravity is in different directions compared to if you're walking down the beach. So these are the things that we're starting to look at.
Rosetta stayed with Comet 67P for more than 2 years. As it ran low on fuel, its final maneuvers were initiated. After a series of lower and lower orbits with Rosetta passing just 3 kilometers above the surface, the probe was set on a collision course with the comet. The spacecraft transmitted pictures and data till moments before its final impact. The 14-year mission had fundamentally changed researchers' ideas about comets' role in the early solar system, and specialists continue analyzing the data. In late September 2007, a new type of spacecraft was coasting away from Earth. NASA's Dawn was the first operational spacecraft equipped with ion thrusters, a refinement of the type used on the demonstration craft Deep Space One. Its mission would have been impossible for a conventionally powered spacecraft. 2 months after launch, Dawn switched on one of its thrusters. It had 2 destinations, Ceres and Vesta, the most massive bodies in the asteroid belt.
Dawn's targets, Vesta and Ceres, are 2 protoplanets left over from the very early accretionary phase of the solar system. And the solar system formed from a nebula of gas and dust that then formed small pieces that created planetesimals, just the smallest building block. And these accreted together to form the bigger blocks and eventually what we call protoplanets.
While ion propulsion systems deliver low levels of thrust, they can operate continuously for months, accelerating the craft to very high speeds.
Ion propulsion really changes the way we can explore the solar system. I mean, it allows us to go to destinations that would otherwise be unreachable, and it allows us to undertake missions that would otherwise be truly impossible.
After almost 4 years and a circuitous voyage of 2.4 billion kilometers, Dawn began the approach phase of its journey to Vesta. Its low approach speed allowed Vesta's gravity to capture it in a high orbit. Vesta emerged as an ancient body with a heavy iron core. Early in its life, it must have been molten, allowing heavy elements to sink, leaving a surface of basaltic rock. These are indications that Vesta formed in the inner solar system with an evolution similar to the rocky planets. Its heavily cratered surface suggests that the solar system's early building blocks were bigger than previously thought. Dawn saw 2 huge craters from ancient meteor impacts that must have come close to shattering Vesta. The larger crater, Rhea Silvia, features a central peak, the solar system's second tallest mountain. In September 2012, Dawn left Vesta, but a problem had developed with the craft's inertial wheels. The electrically powered wheels allow the craft to align itself in 3-dimensional space, and 2 had stopped working. Dawn could continue using its hydrazine thrusters, but their fuel was limited. Xenon, the ion propulsion fuel, was still abundant. Almost 2.5 years later, Dawn was nearing protoplanet Ceres, and its cameras began delivering the clearest images yet seen of the asteroid. Soon, researchers on the ground started to see peculiar bright spots on the surface.
When Dawn found the bright material on Ceres, it was a very unexpected. It was really one of the biggest discoveries that we've made.
Unlike Vesta, Ceres is massive enough to assume the spherical shape of a planet, and it appears to have had a very different origin to Vesta. As Dawn eased towards Ceres, it was gently captured by the dwarf planet's gravity. The very slow changes to the craft's acceleration due to its ion propulsion system saw the spacecraft execute a delicate maneuver, very different to the powerful but brief insertion burn of a conventionally powered probe. Dawn went into polar orbit of Ceres to make its initial geological survey of the giant asteroid. At several different heights, Dawn mapped the surface and determined that the bright spots were sodium carbonate, a mineral directly linked to the presence of water.
Sodium carbonate is not common in the solar system, but we see it coming out of the plumes of Enceladus. We see it in lakes and on Earth and associated with hydrothermal deposits. So it's one of those minerals that tells us a lot about the environment it formed in, and here it was on the surface of Ceres.
The Cassini probe flew through plumes of water vapor emanating from Enceladus, one of Saturn's moons. Enceladus is smaller than Ceres, with a surface of water ice. Scientists think that a liquid ocean exists beneath the frozen crust, heated by gravitational squeezing from its giant parent planet. Ceres was revealing its own evidence of water and a far more complex environment than had been expected.
And what we see with Ceres is that the body of rock is actually alive, and processes are modifying the surface even in the present day. And when we're talking about the bright spots on Ceres, what we're seeing is an indication that there are liquid brines potentially in the subsurface, even in the present day, that are rising to the surface and becoming these bright spots. And that tells us that there has to be a process that is providing energy to drive these fluids to the surface.
Gravitational analysis revealed a heavy planetary core similar to Vesta and larger planets like our own. A final important discovery was the presence of ammonia on Ceres. This led researchers to feel that the dwarf planet had formed in the outer reaches of the solar system, later migrating inward. A direct comparison of the asteroid belt's two largest bodies, made with the same spacecraft using the same instruments, revealed two very different objects with very different origins. When Dawn's conventional hydrazine thrusters ran out of fuel, its mission ended, still orbiting Ceres. Its results forced researchers to rethink their ideas about small, ice-rich bodies. The idea of returning samples from distant bodies to Earth remained enticing. And in 2014, the Japanese space agency JAXA was preparing Hayabusa 2 for its mission to bring small pieces of asteroid Ryugu back to Earth. Hayabusa 2 bears the same relationship to its predecessor Hayabusa as Dawn had to the Deep Space One test mission. The original Hayabusa spacecraft, launched in 2003, did return around 1,500 microscopic grains to a landing site in Australia, but the mission had been plagued by technical difficulties. Hayabusa 2, a refinement of the original spacecraft, launched in December 2014. Though its predecessor had failures in its communications, attitude control, sample collection, and propulsive subsystems, they were well understood, and designers were confident that they had eliminated these flaws. The advantages of ion propulsion for missions to bodies with weak gravitation are now widely accepted. Its destination, Ryugu, is less than a kilometer across, with an orbit that almost crosses Earth's path around the Sun. As Hayabusa 2 approached, its cameras recorded these pictures of the asteroid. Ryugu is a young, carbonaceous C-type asteroid. Remote analysis revealed it as loosely bound rubble. In June 2018, Hayabusa 2 was close to the asteroid and traveling along the same path. It began mapping the surface. The spacecraft carried 4 surface rovers for close examination of surface chemistry, and the initial survey determined where the rovers should be dropped. The largest rover, known as Mascot, is a collaboration between Germany's Aerospace Center and France's CNES. It's a 10-kilogram box packed with instruments. Ryugu's low gravitation means it is able to move by means of an internal weight, and its battery power will last for just 16 hours. Its builders were also involved with the Philae lander, and as soon as results from Hayabusa 2's initial survey were available, they came together.
La réunion s'est déroulée au centre spatial toulousain, tout simplement parce que le plus gros de l'équipe impliquée dans la sélection du site d'atterrissage était toulousaine, en fait, on est basé ici au CNES, et aussi parce qu'on a déjà montré notre expertise au cours de la sélection du site d'atterrissage de Philae. L'objectif principal aujourd'hui, c'était en un temps très court, donc une journée, pouvoir étudier et classer toutes les possibilités pour les sites possibles pour l'atterrissage de Mascot. On en avait une dizaine.
But the team had to compromise between geologically interesting sites and safe places for their lander.
So the most interesting thing is to see the big boulders from the vertical structure. So we really can look into the cracks. We really can look if there is some layering in it. There are many boulders on Ryugu, so I'm pretty sure we get a good view of this interesting part of this asteroid.
On a intérêt à ce que le site ait la température la plus basse possible, parce que plus le site a une haute température, plus la surface va émettre du rayonnement qui risque de masquer les signatures spectrales qui vont nous donner accès à la composition. Donc on cherche un endroit qui soit relativement froid, ce qui est difficile parce que c'est un objet extrêmement sombre, relativement proche du Soleil, et tout le monde sait que quand on a un objet très sombre proche du Soleil, il chauffe beaucoup parce qu'il retient l'énergie qu'il reçoit du Soleil.
The blue region on Ryugu reveals the intended landing area. It was designated MA9, but nicknamed Alice's Wonderland. Hayabusa 2 descended to 41 meters above the surface, lower than intended, before it released the Mascot probe. The gravitational force experienced by the probe was equivalent to a piece of paper dropped from a height of 30 centimeters. As it fell, it captured images of Ryugu. Six minutes later, Mascot made its first impact, tumbling across the surface for a further 7 minutes before coming to rest. During its brief period of activity, Mascot relayed more images. There were two types of rock, one smooth with sharp edges, the other highly textured and fragile. And although there were small fragments, there was no dust. Hayabusa 2 was equipped with an impact-absorbing sampling probe for retrieval of material from the surface. And early in 2019, it descended to collect its first specimens. It collected so much that a subsequent similar landing was cancelled. Yet there was one further collection swoop of a different nature remaining. In April 2019, Hayabusa 2 released a free-flying explosive charge. It was designed to fire a copper projectile into the asteroid, so material that had been hidden beneath the surface could be exposed and then collected. Then Hayabusa 2 moved out of harm's way. The projectile made a crater 10 meters across, which was examined closely for several months. Finally, Hayabusa 2 dropped a reflective target marker to help guide it to the crater. And a month later, the spacecraft descended for its final sample collection. It was successful, and the samples were stored separately from those gathered earlier and then transferred to the sample return capsule. After 17 months at Ryugu, Hayabusa 2 began its long journey back to Earth, arriving late in 2020. Its sample return capsule was released, safely re-entering the Earth's atmosphere and landing in the deserts of South Australia. Analysis of the samples has begun, but results are not yet available. In 2016, NASA's OSIRIS-REx was launched on a very similar mission. In 2018, it arrived at asteroid Bennu and began a detailed survey of the asteroid's surface. Bennu is classified as a rubble pile. That is, it is formed from debris loosely held together by its very weak gravitation. Just like Hayabusa 2, OSIRIS-REx is a sample return mission. The scientific team controlling the mission had to rethink their original plan when they saw just how rough Bennu's surface is. Because there are no large open areas, the team had to refine the probe's landing accuracy. OSIRIS-REx had to match its orbit to Bennu's rotation and deploy its sampling arm. At the end of the sampling arm is a circular head designed to trap swirling particles dislodged by a blast of nitrogen. Late in October 2020, it began a slow descent to an area near the asteroid's north pole that had a combination of interesting geology and favorable landing conditions. Landmarks were used to fine-tune the probe's point of contact, and its solar panels were splayed back to reduce its profile. The probe had to act autonomously and touched within 1 meter of its target. When Mission Control received confirmation of a successful sampling, they were pleased. But it took longer to realize that perhaps it had been too successful, as an abundance of material was clogging the sealing mechanism on the sampling head, with material being lost. The collection head was stowed in the return capsule, with a spin procedure to weigh the sample cancelled for fear of losing more material. OSIRIS-REx is due to deliver its precious cargo back to Earth in 2023. As astronomers discovered more asteroids and comets and plotted their orbits, they established a special category, the Near-Earth Objects, or NEOs. Knowing how easily these bodies' trajectories can be perturbed, and also with an awareness of past meteoric impacts with Earth, both the UN and NASA established coordinating networks to pool knowledge about NEOs. The emphasis has shifted from pure scientific curiosity to the early detection of anything that could threaten the Earth. The Catalina Sky Survey is one of several projects searching for NEOs.
It starts with discovery, goes on to follow-up and characterization, impact risk analysis, mitigation studies, but you can't follow up and you can't characterize and you can't calculate the impact risk of something you don't discover.
Telescopes around the world will catalogue information about sightings of new objects. Late in 2017, the Pan-STAR Survey Telescope in Hawaii discovered something unique. An object was traveling so fast it was not bound by anything in the solar system. Eventually called Oumuamua, Hawaiian for Advanced Scout, it is the first recorded visitor from beyond the solar system.
We think this object is very long, perhaps 400 meters or so long, and very narrow, skinny, perhaps maybe 40 meters or so in the other dimensions. That's a very unusual shape. We don't see that in our solar system. None of the asteroids in our solar system look like that. So it's very puzzling how it could have obtained this shape.
At NASA's Jet Propulsion Laboratory, the Center for Near-Earth Object Studies concerns itself with computing high-precision orbits. Any possibility that a large object could strike the Earth will trigger warnings and prompt more detailed studies, but so far that is all that can be done. Deflecting an asteroid on a collision course with Earth has been confined to science fiction. Now, a collaboration between NASA and ESA, called AIDA, will make the first attempt to alter the course of an asteroid. Researchers have chosen the binary asteroid system Didymos as their target, because it's close yet poses no threat to the Earth. Didymos is around 800 meters across. Its moon, known as Dimorphos, is the body NASA is hoping to move. DART, the American part of the mission, will start its journey in mid-2021. It's a simple impactor equipped with a navigation camera to autonomously guide it to a head-on collision with Dimorphos. The impactor will hit at 6.6 kilometers per second, possibly leading to a change in velocity for Dimorphos of 0.4 of a millimeter per second. The European part of the mission, Hera, is not scheduled to launch until 2024. When it arrives at Didymos, it will accurately measure changes to the speed of Dimorphos and the size of the impact crater, vital information about the first attempt to alter the course of a celestial object. The US government has set the goal of identifying 90% of the massive asteroids that cross the Earth's orbit. No known large objects have a significant chance of hitting the Earth within the next 100 years, but it is conceded that we may only have detected half of the large bodies that could threaten our planet.